oligonucleotide design for Exon for about 20 years. And she'll talk to you about how to do this in detail. Over to you, Annemieke.
Okay, thank you, Petra, and thank you also for arranging this and coordinating this webinar. As you can see on the first slide, I was supposed to give this presentation in September at the OTS meeting in Bordeaux, but unfortunately I was unable to attend. So I'm very happy that this has allowed us to kick off this webinar series with this topic of oligo design for exon skipping. Some disclaimers first. So of course there's two ways to do the design or to get your exon skipping oligonucleotides. And if you have limitless funds, the best way is just to do an oligo walk for your target exon and then have a series of oligonucleotides and just test the ones that work. However, most academic groups will not have limitless funds, so they will be able to buy maybe 2 or 3 or 4 oligonucleotides only, and then it's good to have a rational design. And this is what we have done. So I have designed over 300 oligonucleotides, the majorities for targeting dystrophin exons, and we have analyzed these oligonucleotides in retrospect and then compared the ones that do work with the ones that don't work. And that has given us some ideas of what parameters to look for in an oligo that can at least help increase the chance that it will work. Having said that, each exon is unique. There's no guarantee that the designed oligonucleotides will work, even if you adhere to all the guidelines. But still, if you the chance that your oligonucleotide will work is increased. And there's also several papers that I can refer you to if you want to go into the detailed analysis of how we reached these guidelines. So then the first thing to consider is the chemistry of the oligonucleotides. And of course, the oligonucleotide, if you want to develop it as a therapy, it needs to be stable. If you just use RNA or DNA, the stability is mere seconds in vivo because of all the endo and exonucleases present in the cell and in the serum. So you need chemical modification to make them more stable. And most currently available chemical modification are resistant to endo and exonucleases. So this is easily achieved. Then the second consideration is that the oligonucleotide need to be resistant to RNase H cleavage. We're not trying to knock down something, we're trying to modulate the splicing. Most 2O modified or all 2O modified oligonucleotides are RNase H resistant, and most third generation chemistries like the peptide nucleic acid, morpholinos, locked nucleic acids are also resistant to RNase H. So it's not that hard to find these chemistries, but it is something to consider. Then the third thing is to consider the pharmacokinetic properties. So the phosphorothioate backbone is a double-edged sword. So on the one hand, it gives good pharmacokinetic properties to the oligonucleotides because the phosphorothioate backbone makes that the oligonucleotide will bind to serum proteins. And those will act as a carrier and prevent clearance, because we have to remember antisense oligonucleotides are very small, and as all small things, they will be filtered by the kidney very efficiently. So having a phosphorothioate backbone prevents renal clearance because of the low affinity serum binding, and that means that then the oligonucleotides can be taken up by tissues. Having said that, the main driver of toxicity is also the the phosphorothioate backbone. This is a bit of a double-edged sword. If you don't use the phosphorothioate backbone, so for instance with the morpholino chemistry, that means you need a lot higher doses. So this is a consideration. So then the next consideration is the thermodynamic one. because the antisense oligonucleotide needs to be able to bind to its target in order to, because what an exon skipping antisense oligonucleotide does is it binds to the target site and thereby prevent binding of splicing factors that can then recognize the exon and bring about splicing. So it needs to properly bind in order to prevent that the exon is recognized. And this seems really logical, but it's definitely something to consider. And the first thing to consider is then the secondary structure of the target exon. And we generally use the mFold software, which is available online, to do this prediction.
Now what happened? Everything ran well during the test. But suddenly my audio seemed to have failed. Apologies for this. I'll restart where we left off. So I was explaining about the thermodynamic considerations for exon skipping oligonucleotides. It's important that the oligonucleotide is able to bind to the target sequence. And the first thing to consider is the secondary structure of the target exon. And we use the mFold system for that. And as I explained just before I got disconnected, is that the mFold system will provide you with several structures for each exon. And it also gives you the SS count. And what the SS count gives you is the total number of structures, and then per nucleotide, the number of times that oligonucleotide is single-stranded. So if the SS count is high, that means that there is an open part in the exon. And if the SS count is low, that means that there is a closed part. For instance, here you can see the SS count is 0. That means that that nucleotide is always connected to another nucleotide in the secondary structure, while if it's very high, then generally it will be open. Why is this important? This is important because we think that if you have a closed structure like here, it may be very hard for the oligonucleotide to bind, because it needs to disrupt this closed structure. On the other hand, if you have an open structure like here, the AON is probably able to bind quite well. But the question is whether that will lead to exon skipping, because it's unlikely that this will change the secondary structure. And the idea is that not just the motifs matter when an exon is recognized, but also the secondary structure. So ideally what you want a partly open, partly closed structure, because then the oligonucleotide will be able to bind, but it will also disrupt the secondary structure. And so that is usually how we design our oligonucleotides. But then there's other consideration to take into account. The first one is the second one is the percentage of GCs. And probably everyone listening will know this, but I'm reiterating it. An A and a T can bind with 2 H bridges, while a G and a C bind with 3 H bridges. And this is why a G and a C bind with a higher affinity than an A and a T. On the other hand, having a lot of G and C does not seem to be optimal. So you need a certain amount because the oligonucleotide needs to bind. However, if you have too much, that seems not to be optimal. And if I look at my oligonucleotides that work, then it really seems that the optimal is between 40 and 60% of GCs. Also for the TM, so back in the olden days when we did this analysis, there were no predictions for modified nucleotides. So we used the predictions for DNA, so the online calculators for DNA. And we found that ideally you have a melting temperature of at least 48, which probably for the modified oligonucleotides might be slightly lower, slightly higher. But it seems that a GC percentage between 40 and 60 and a TM of, for DNA, at least 48 is best. That has repercussions for length. And I want to say something about length here, because if you test your oligonucleotides in vitro, and especially if you use a transfection reagent and a phosphorothioate backbone, the transfection efficiency will be very high. So if you make a longer oligo, then the TM will, of course, be higher. The oligo will bind better to the target. So longer oligos in vitro will generally work better than smaller oligos. However, when you go in vivo, if you have longer oligos like 30 or 40 or even 50 mers, in vivo, these often are less effective. And this can have several reasons. For instance, they will bind a lot better to the phosphorodiol, so maybe this low affinity binding now becomes a higher affinity binding, so it becomes more difficult for tissues to take up the oligonucleotides. And another thing is that if your oligonucleotides are longer, they may be able better to bind to each other. And this is the third consideration, the tendency of the oligonucleotide to form self-structures or self-cell structures. And you have to not only check whether your oligonucleotide can bind to itself, and if you have, so the general oligonucleotides for exon skipping will be between 18 and 22 nucleotides. Generally, these oligonucleotides will not bind very efficiently to themselves. So the cell structure, if you have smaller oligos, can usually be avoided. However, when you give a mix of these oligonucleotides, they can, of course, also bind to their counterparts, as you can see here. So this is using RNA structure, which is another available software online. You can calculate how efficient the oligonucleotides can bind to their counterparts. And if you have a lot of if you have longer oligos or if you have very DC-rich oligonucleotides, what you will see is that these cell structures have a very low energy. So they are very energetically very stable. And then that makes it more difficult for the oligonucleotide to bind to the target. It will probably just prefer to bind to its counterpart. Also here, like with the GC percentage, there is a balance. If the oligonucleotides have some cell structures that are not very energetically stable, so somewhere between -5 and -15, these oligonucleotides generally work better than those that have a more stable self-structuring or a less stable self-structuring. And we have no scientific proof, but the hypothesis is that if they form two energetically stable self-structures, then of course they start to aggregate, they will bind to themselves and will be unable to bind to the target. If they are not forming any self-structures, they may be binding to whatever RNA they encounter when they get into the cells. So then it probably having some self-structure will prevent them from a specific binding and increase target binding. However, as I said, this is our speculation. We've never been able to scientifically prove this. So then the third or the fourth thing, and you can also do this with RNA structure software, is to see how well the oligonucleotide can bind to the exon. And so you see here the free energy of the exon is calculated as -27. And if you have the complex of the exon with the AON, you can see that it is a much more stable structure. And more stable generally means that better. And I try at least to have an increase of about 20. And again, yes, you can artificially make this better by designing a really long oligonucleotide, but there is a limitation there. So I would say ideally you would want this to be, you want your oligo not to be too long and not to be too GC rich, while still fulfilling all the other criteria. So then, if you have a choice of target exons, there's also some recommendations. So generally, or for some people, there may not be a choice. If you target a cryptic splicing splice site, or if you target a specific exon, that is your exon, and you will have to work with that. However, sometimes you do have a choice. For instance, if you want to use exon skipping to achieve knockdown. If you do this, then there are some things that may help you. So, for instance, shorter exons generally are easier to skip. So, if the exon is between 100 and 300 nucleotides, this is generally optimal. If the exon is really short, it's more difficult to skip. Probably also because it's more difficult to find target sites. There's not a lot of room to optimize. If you have longer exons, it's more difficult to skip. Probably because if you target one site, there may be other sites that can still make that exon recognizable by the splicing machinery. So obviously, if you have the choice, avoid exons that have high similarity with other sequences somewhere else in the genome. Exons that have long introns are easier to skip than exons that have short introns. And this probably has to do with dynamics. So if the intron is very short, probably splicing is very quick. And for the exon to be skipped, you want the oligonucleotide to bind to it before the exon is spliced. So if splicing happens really quickly, then probably the AON will bind too late, and then you've missed your opportunity. If the flanking introns are longer, then probably splicing will also take longer, so it's easier to find an oligonucleotide that will induce exon skipping. If the splice sites are very strong, obviously it's more difficult to skip the exon. If you have an exon that has a very high GC percentage, that makes things more complicated. But like I said, sometimes you just don't have a choice. Having said all this, so far it has been possible to skip all intended exons. However, having said that, sometimes you will need a combination of oligonucleotides, especially for long exons. Sometimes you will need 2 oligonucleotides to achieve efficient exon skipping. So then another consideration is where to target. If you want to modulate the splicing, the first thing you will think of are the splice sites. However, of course, within the exon, there's also exonic splicing enhancer sites, and these are also good target sites. We prefer to target exon internal sequences, and I have given the reasons here on this slide. First of all, they give you more flexibility because you have the whole of the exon to work with rather than just the acceptor or just the donor splice site. Introns, of course, have lower GC percentage than exons, and introns generally have quite a low GC percentage, so it's easier to get or to design an oligonucleotide with a GC percentage between 40 and 60%. If you target the exon than if you target the splice sites, which are partly introns. Another consideration is that the exons are more specific. So, of course, especially if you target the acceptor splice sites, there will be a polypyrimidine track. So it will be more difficult to find or to design an oligo that is specific and that doesn't have a lot of overlap with other target sites. There's also a better chance to be effective, and we've actually tested a large set of oligonucleotides that were designed by a colleague in Australia, Steve Wilton, and he had more than 100 oligonucleotides targeting either exons or splice sites. And what we saw was that the oligonucleotides targeting the exons had a larger chance to be effective than those that targeted the splice sites. And we think also that is because the splicing factor, so the U1 and the U2, probably bind with a much higher affinity than the splicing factors that bind to the exonic splicing enhancer sites, because these are much less well defined. The enhancer sites are motifs, while the splice sites have a much stronger consensus. So if you indeed want to target the exonic splicing site, you can use, for instance, human splicing finder software. And I like to use this because it combines different other prediction programs. And like I said already earlier, sometimes for some exons you need a combination of oligonucleotides, for instance, targeting each of the splice sites or targeting an exonic region and a splice site or targeting 2 exonic regions. Sometimes for some difficult exons, that is the only way to induce exon skipping. So this is what the human splicing finder software looks like. And well, this is very easy. You say analyze the sequence, you paste your sequence. The only thing to bear in mind is that you have to use T's rather than U's because the software only recognizes T's. If you use U's, it will filter it out, and then you end up with a much shorter exon and with motifs that are not really truly in your exon. So this is the output. So like I said, it looks at different prediction softwares. So the ESE finder, rescue ESE, PESE, and I like it because you have everything in one go. Of course, these are all predictions. So that makes things challenging. However, generally what I think is that if things co-localize, so for instance here, here you have a lot of rescue ESE finder motifs, you have rescue ESE motifs, you have PESE motifs, all locating in roughly the same sequence. Well, then I think it's likely or more likely that indeed in this sequence there will be an exonic splicing enhancer, and that will be a good target site. However, of course, this image will differ for each exon, and sometimes it's very clear there will be only one region where you have a predicted exonic splicing enhancer site. Sometimes the whole sequence will be riddled with these exonic enhancer motifs, and then it's more of a guess, and you'll have to make do with the other considerations. There's also exonic splicing silencer sequences and motifs that are predicted. And we've looked at this as well. And for the exonic splicing enhancers, what we see is if you target these, the likelihood that your oligo will be effective is higher. Whether you target the exonic splicing silencers or not does not seem to matter. Of course, this is primarily based on dystrophin exons, so I'm not sure whether it's a general rule. But another consideration is that the motifs for exonic enhancer sites and the motifs for exonic splicing silencer sites are sometimes more difficult, or are sometimes similar. So that makes things complicated. So take-home message: focus on the exonic splicing enhancer sites and use that to target sites. And I've circled certain sites that I would find interesting in this exon. So then the next topic, and that is the off-target effects. So if you take all these things into consideration, generally you will end up with a couple of locations that may be of interest, and then you can use that to get your oligonucleotide, which is around 20 nucleotides long, which has a GC percentage of between 40 and 60, which has good thermodynamic properties, which has good self-self dimerization, not too much, not too little. But then there's another thing. To check whether there is homology anywhere else in the genome. And ideally, you want no homology with anything except the target. However, generally, there will be some homology. And as a rule of thumb, I usually try to avoid more than 50 nucleotide homology. And here you have to bear in mind that this also depends on the chemistry that you're using. So if you're using, for instance, an LNA modification, which has a really high affinity, then a 50-mer may already bind to its very high affinity. If you use the 2-O-methyl phosphorothioate or the 2-O-methoxy methyl phosphorothioate, probably a 50-mer will not be able to bind very well. Another thing to consider is that a mismatch in the center is much more disruptive than a mismatch at the end. So you can see here there is a 17 nucleotide overlap. You can see here the top one looks worse because there's 20 nucleotides overlap with one mismatch. However, if you would calculate the affinity for the top one, it's lower than for the bottom one because there's a consecutive stretch of homology. So these are things to take into account. If this can be avoided, please avoid it. But of course, sometimes one cannot. So then the question is this a problem? And often this will not be a problem. So the first thing to consider is the off-target sequence located in a gene? If it's not, then probably it will not be problematic. If it is in a gene, then the next question is it in a gene that is expressed? And well, if it's not, then it's probably not a problem. So if it's expressed, is it in an exon or is it in an intron is what I mean. Well, if it is in an exon, then the next question is, what is the target tissue of your oligonucleotide, and where is the gene that you potentially target as well? Where is it expressed? Is it expressed in the liver or the kidney? Well, we know that the oligonucleotides upon systemic delivery are very highly taken up by these tissues, so that might be a problem. If it's in the brain and you use systemic delivery, we know that there's hardly any oligonucleotides taken up by the brain, so that probably will not be a problem. Vice versa, if the gene is expressed in liver and kidney, but you're targeting the brain, then we know that there's not that much of the oligonucleotide that is then taken up by the liver and the kidney. So it's, again, less likely to be a problem. And then also something to consider is the timing. If it's a gene that's only expressed in embryonic tissues and you're treating children or adults, again, probably this won't be a problem. So then if you use, for instance, systemic delivery and your off-target is expressed in liver, then the next question to ask is, what will happen when the exon is skipped? Because exon skipping generally happens only at very low levels. So you will not get a huge knockdown of this gene. You may get a minor decrease in expression, which probably will not have any effect at all. The only exception is if you expect a dominant negative effect, because here even a little bit of protein may have toxic effects. So if you take all these considerations into account, then probably generally the conclusion is that it does not really matter that much if there is a sequence with some homology. Another thing is that it's good to look, because once you know where to expect it, you can monitor it. So you can actually check whether you indeed do see an effect, whether you do see exon skipping or not. So that was the last slide. If you want to know more, there is a chapter published in a book that I edited on exon skipping, and here you can find all, say, a protocol with all the different steps of how to design an exon skipping oligonucleotide, really step by step, all the small considerations that I couldn't discuss here. I think this book is available through the library of many academic institutions, so you may have access to it. If you don't have access to it, then drop me an email and I can see whether I can give you a PDF of just a chapter. So with that, thank you all for your attention. Apologies again for the technical difficulties that we faced. Of course, we did not have this in the trial run, but we did have it here. So thank you for your patience, and I think now we can open it to questions. I'm happy to answer your questions.
Oh, wow, I really got video back. So any questions, please put them in the chat box. With about 70 attendants, it would be just too much background noise if we opened up the floor. So the first question was actually from Art Levin, and he would like to know, how do the predictions of human SciFinder compare with the modeling done by Echegoyen et al.?
Well, then I'm sorry, but and I would need some extra information of the modeling done by Echegoyen, because I don't know which modeling that is. I know that the human splicing finder takes several models into account separately, so it may actually take this into account already, but I'm not sure, because I know them by what they call them, so ESE Finder, and I know that one is from Adrian Krainer, but I don't know. So I don't know which modeling this refers to. So maybe Art can elaborate.
Okay, I can try and open the floor. I need to find him in the attendant list. Art Levin, there we go. Art, I will open the. You're now on voice, Art. waiting for
But
you.
he's still paying attention. Otherwise, we can maybe go to next question and wait until Art is typing.
Okay. The next
so maybe
question.
take a few other questions. And meanwhile, Art can elaborate. So there was another question about the thermodynamic consideration for exon inclusion. So the thermodynamic considerations for exon inclusions are not different because the same thing applies. The oligonucleotide has to bind to the target sequence. There is, however, one difference, and that is that generally, if you want to achieve exon inclusion, it is better to target intronic regions. The reason for this is that if you target an exon, then the exon that is included may still bind, have the oligo bound to itself. So in the end, you will end up with a transcript that has the exon that you want included, but also the oligonucleotide bound to it. Whether this will have an effect on translation or not, we do not know. But generally, people say it's a risk that you should try to avoid. So that means that then, generally, what you will target are introns. And then, of course, you end up with lower GC percentages. But still then, the considerations apply that you need an oligonucleotide that has strong enough affinity to bind. So ideally, the GC percentages should be, for an intron, if you can get to 40%, that's already a good achievement. You need to find the good target site, of course. You need to avoid the self-cell structuring, etc.
Annemieke, Art is now on voice.
Okay. So Art, please elaborate.
So the model that you're going has is a really nice. It's a couple of nice papers from that group where they demonstrate high dependence on position, and it's actually distance from the splice site, and that seems to be highly dependent, and there's a relationship between TM and distance from the splice site. So I was just wondering how well the Finder software predicts for that. And then the second question, which is one that Nano has a question on melting temperatures.
So I'll get first to your first question. So that's actually a very interesting point. So the human splicing finder does not take distance from the splice site into account. What we have seen, however, and in view of time, I did not discuss this here, but I'm very glad that you asked this question. What we see is that oligonucleotides targeting the start of the exon, so beginning, say the first 20-30% of the exon, have a much higher chance to work than oligonucleotides targeting anywhere else. So if you target close to the 3' splice site, so the acceptor splice site, which is the start of the exon, you're much likelier to find an effective antisense oligonucleotide than if you target the middle or the end. So it seems to be mostly proximity to the acceptor splice site that helps get you an effective oligonucleotide. And also here we were speculating that again it's probably a timing effect. The exon will not be spliced until, of course, the end of the exon is produced and the second intron or the second splice site is there. So probably the window of opportunity is better if you target at the beginning of the exon than at the end of the exon, because you want to beat the intron being removed. And I think so. The optimum TM. This again is a good question. So I think the problem is that we have only been able to look at the TM predicted for DNA oligonucleotides while we were using 2-methylphosphorothioate oligonucleotides, and that was just because back in the olden days there were only prediction programs for DNA and not so much for the modified oligonucleotides. With that, we see an optimum of around, say between 48 and I would think probably 58 and 60. How that translates to the different chemical modifications, I do not know. And I think probably it will differ for different chemical modifications. And I would assume that for instance, for a log nucleic acid, you don't want a very high, I mean, it already small oligonucleotides will have a high TM. So I think probably it's the same thing as with the GC percentage. You don't want your TM to be too high. Also, because if your TM is high, that means that also the self binding will be more optimal. And then the purine track. So Mano also asked whether the purine track is a problem. When we started designing our oligonucleotides, I hear an echo. Can Petra, can you maybe mute your line?
Yes, sorry.
Okay. Yeah, this is better. So no, maybe my audio is now working. Maybe that's it. So no, now it's there. So when we started designing our oligonucleotides, again back in the olden days, exonic splicing enhancers were really not very well defined. And what we generally would target was purine-rich sequences, because, well, these were the first exonic splicing motifs to be identified. And we found a lot of effective AON. So the purine track does not seem to be a problem. Having said that, it also depends on the amount of adenine in there. If it's very A-rich, then it is a problem, because then it's really difficult to get an oligonucleotide that has a TM that's good enough. The solution then is to make a longer oligonucleotide, but then of course if you start going in vivo, that is not that's more challenging. I think we've really seen that longer oligos in vivo have more phosphorothioates, and what this means probably that they will bind to the serum proteins better, and that may reduce uptake by the target tissue. But of course, having more phosphorothioates also leads to more side effects. So then the next question is, how about an RNA walk? Is it more reliable than the software, than the prediction software? I think if you can do, and I assume that with an RNA walk you mean an oligo walk, so you design the different oligos for the target. If you have the possibility financially to do an oligo walk, then this is better. I mean, this will be much more informative, and it will also, because now we may exclude, we look at it rationally, we may exclude sites that are actually quite good. So if you can afford an oligo walk, then I would do an oligo walk. However, often, especially academic groups, will not be able to do an oligo walk. If you have an exon that, for instance, is 300 or 400 nucleotides, and you want overlapping antisense oligonucleotides, this is a lot of antisense oligonucleotides to test. So yes, it's more reliable, but the main reason for doing this design webinar is for the people that cannot afford to do an oligo walk, because, well, if you cannot do it, then what is the alternative? And the alternative, hopefully, is some rationality that I have been able to provide you. Then the next question is about chemistry, and the question is, do you think that all the chemistries are equally good to design and produce splice switching oligonucleotides? I think probably yes, in theory. What the oligonucleotides have to do is to prevent the splicing factor from binding. If the oligonucleotides can bind to the target RNA with sufficient efficiency, they can do this. Of course, there's other considerations to make for the different chemistries. And I went over this a little bit. So if you have a phosphorothioate backbone, you will have better pharmacokinetic properties than if you do not have a phosphorothioate backbone. The PNA, for instance, has very poor pharmacokinetic properties as far as I'm aware. So in vivo delivery is a big challenge there. And of course, what we generally do when we design exon skipping oligonucleotides is that we want to develop them as a therapeutic moiety. So then if the pharmacokinetic properties are very poor, as they are for PNAs, that limits their use. Morpholinos, of course, have been used, and in fact, the first exon skipping oligonucleotide that was approved as a therapy is a morpholino, so that's etoplursen. So this definitely works. However, because it doesn't have a phosphorothioate backbone, that means you need a much higher dose than you otherwise would need. Another consideration is if you want to test these oligonucleotides in cultured cells, then the 2-O-methyl and the 2-methoxyethyl oligonucleotides are much easier to work with. Generally, they're cheaper, but also you can use them, you can transfect them because the PNAs and the morpholinos are not charged, and therefore it's much more difficult to transfect them. You can add them to the medium at really high doses and see whether the oligonucleotides are effective. But with the 2-O-methyl and the 2-O-methoxyethyl phosphorothioate, you can transfect them already at low doses and just see whether your oligonucleotide works. You can also use that to find your target sequence. Actually, so etoplursen that I just mentioned, so this is an oligonucleotide approved for Duchenne muscular dystrophy to target exon 51. How this target site was identified was with 2-O-methyl phosphorothioate, targeting that exon, and then the best target site, they made several morpholino oligonucleotides targeting several locations, and what it turned out was that the best target for the 2-O-methyl phosphorothioate was also the best target for the morpholino oligomer. Other things to bear in mind are that generally it's not so that you can make a one-to-one counterpart. So morpholinos often are slightly longer because they have a slightly lower affinity than the 2-O-methyls. LNAs, the log nucleic acids, generally are shorter because they have a higher affinity. So this is something that you have to take into account. So you can use all chemistries probably, but you have to be aware of the specifics of that chemistry and take that into account when you design your oligonucleotide and when you test it, and also already bear in mind the translatability. So there may be new chemistries coming up, and they may work really, really well in cultured cells, but if it's impossible to produce enough to treat a single mouse, it's also impossible to produce enough to treat a human. So that's another thing to consider is the manufacturing and the upscaling. So the next question is, can you provide a statistical analysis of the data, or should they be considered rules of thumb? Well, actually, I would like to refer you to several papers that we've written, and if you look into the oligo design chapter that I've written, these publications are cited. So we have done statistical analysis comparing oligos that work and do not work, and the guidelines that I presented here are distilled from those analyses. So it's not rule of thumb. We actually did statistical analysis, and probably afterwards. So this webinar will be put online, and I think we can probably put the references associated with it there as well, because I think that is probably useful for you all. Then the next question is about with the advent of delivery system, the need for phosphothioate linkages is definitely changing. Yes, Art, I agree with you, and I think this is also a good development because, like I said, so the phosphorothioate is great, and it gives great pharmacokinetic properties to the oligonucleotide, but it is also the main driver of toxicity. And I think it's also for this reason that people are looking at alternatives to hopefully make these linkages a thing of the past. I think for now they work well, and I think they've definitely brought the field where it is now. But hopefully in the past these linkages can be avoided by delivery system or maybe even other conjugates or other chemistries that don't need the phosphorothioate linkage. Let me see other questions. So, are there reliable parameters to consider to ensure that the morpholino sequence, splice switching oligo sequence for a given target will produce the same in vitro splice modulation as a phosphorothioate oligonucleotide? Is only a longer sequence needed? So far, this is based on less oligonucleotides, but so far for the Duchenne field, we, and not just me, but other collaborators in Australia and in the UK, we have compared to a metal phosphorothioate and morpholino oligomers, and it really seems that generally the best target site for one chemistry is also the best target site for the other chemistry. However, there's also probably some chemistry-related things that you have to consider. So length is definitely something to consider because you need the proper affinity. Another thing is that certain motifs may be toxic for one chemistry but not for the other. So maybe a motif to avoid for the morpholinos may not be the same motif to avoid for the 2-O-metal phosphorothioate. So I think that's the only consideration that I can think of that may change a target site. But generally, so far, a good target site for the 2-O-metal phosphorothioate is also a good target site for the morpholinos. Yeah, so Mano mentions that conjugates may be useful. So I'm only reading this now, but I already mentioned conjugates. So I agree. Conjugates will be useful, and there's two types of conjugates. There's the one that improves delivery in general, but there's also conjugates that help the tissue-specific uptake. And of course, we have the GalNAc that improves delivery to liver cells a lot. Hopefully, there will also be others in the future that help with the uptake into other tissues. So, for instance, we're working on muscle. We would love to have conjugates that improve delivery to muscle. So far, whatever we test, if it's improved uptake in muscle, generally it will be much more improved uptake by liver. So I definitely agree, and I think conjugates really will be something to develop further in the future. So the next question, do you consider the chemistry for potential impurity profiling at oligo design? So I'm not sure what that means. Generally, what I do is order 2-O-metal phosphorothioate oligos because they are the cheapest and the easiest to test in vitro. And of course, also the ones that are already tested in clinical trials. So when I consider a chemistry for an exon skipping drug, there's things that I think to consider for me is whether it works. The second one is whether you can increase the manufacturing to such amount that you can use it in humans. And maybe there the impurity is something that you mean, because if upscaling is difficult because, for instance, you get a lot of impurity, so the yield is not that high, then this can be a problem. And one other thing to consider is how much is already known about the oligo and whether it's already used in humans. So if it's a chemistry that's very similar to something that's already used in humans, I think it's more likely that it will be safe than it's a completely new chemistry and that it may or may not be safe. And I'm not saying that we should therefore exclude that oligonucleotide, but I do think that safety then should be ideally established early on, rather than say when there's a lead compound already highly fast advanced and clinical trials already being prepared. I think we should confirm safety earlier, but that's my personal opinion. Any other questions? If not, I hand back to Petra.